This is 3.2 Properties of Solids. So our outcome is I can explain the relationship among macroscopic properties of a substance and the particulate level structure of the substance. So the beginning of this starts out with some notes, and then we get into the questions, and we've got completing this table to compare types of solids. So the different solids here are going to have different forces of attraction, which is going to impact their properties like melting point and malleabilities. So an example of an amorphous solid would be something like glass. If you've looked at really old glass, it actually looks like it started to melt. And that's actually because of the amorphous nature of the gas. Over time, those bonds have shifted. Plastic, also amorphous, and chalk actually has an amorphous structure. Now, atomic metallic, these are going to be our metals like iron and steel. Atomic network are going to be things like carbon. So they're made of covalent bonds, but they form kind of large networks of atoms. So that would be like the carbon in a diamond. Molecular is going to be also covalent bonding. Molecular solids are like solid water and iodine. So just those covalent molecules that are solids. And then ionic, an example is like sodium chloride. So they have very strong attraction between those particles, which is why they have such high melting points. Some examples would be sodium chloride, also marble. So I want to point out that chalk and marble both have the same chemical formula. The difference is in the structure. So they have very different properties because of the way that the calcium and carbonate is arranged. So using the table, classify the following substances. So gold is going to be a metallic solid. Carbon dioxide is a molecular solid. Lithium fluoride is ionic. It's made of lithium and fluoride ions. And krypton would be an atomic network solid. So our reflection questions: why are ionic compounds poor conductors as solids, but good conductors when dissolved in water? So as solids, all of those ions are stuck together and they can't move. So they can't carry any charge. So they're going to be poor conductors until you dissolve them in water. Suddenly now those ions are free from each other and able to move and carry energy or carry charge with them. So how does the boiling point relate to the strength of interparticle attractions in a solid? So it's not as clear of a relationship as we see with melting, because once we're boiling, we're going from liquid to gas, and those interparticle attractions change. But in general, as those interparticle attractions become stronger, then the boiling point is going to be higher.